A single long prompt can make the token generation slow down for the requests that are already running on the same GPU. Suppose three users are already receiving the streamed responses. Their requests are in the decode phase. So the model is generating one token for each active sequence and then next token for each active sequence, and model is continuing like that. Now a fourth request arrives with 8000 token prompts. Before model can generate its first output token, model has to process the entire prompt, and that part is called prefill. And there are requests that are already active and need its next output token. That part is called decode phase. Both kind of work, prefill and decode, needs the same GPU. So inference scheduler has to decide how to run them together on the same GPU. Before looking at the scheduling problem, let us quickly separate the two phases, prefill and decode. During prefill, the model processes all the tokens in the input prompt and create the KV cache for them. If the prompt contains 20 tokens, it completes quickly. If the prompt contains several thousand tokens from a long conversation, from RAG results, or an agent context, prefill becomes much larger operation. Once the prefill is complete, the model can produce the first output token. The time the user waits before seeing that first token is called time to first token, or TTFT. That includes any time spent waiting in the queue as well as the time required to process the prompt. After the first output token is generated, the request moves into decode phase. During decode, the model generates one token, adds that token to the sequence, and then uses it to generate the next token. This continues until the response finishes. For the user, decode quality is visible in the gap between a streamed token. If tokens arrives regularly, the response feels smooth. If there are long pauses between them, the response feels slow, even though generation is still progressing. So prefill affects when the response starts, while decode affects how smoothly the response continues. Prefill is usually one larger block of prompt processing work. Decode consists of many smaller repeated steps. That difference is where the scheduling problem begins. Let us go back to the same example. Three requests are already decoding and a new request arrives with an 8000 token prompt. One option is to process the full prefill immediately. The GPU starts processing the new prompt and continues until all 8000 tokens have completed prefill. This helps the new request because it gets closer to producing its first output token. But while the long prefill is running, the three existing requests are still waiting for their next decode step. Their response may have been streaming normally, and then the user suddenly see a long pause before the next token appears. The new request gets prompt processing time, but the active streams experience worse inter-token latency. The scheduler could take the opposite approach and continue running decode first. That protects the user who are already receiving responses. Their tokens continue arriving regularly, but the new request remains in the queue because its prefill has not started yet. If new decode work keeps appearing, that long prompt may wait through many scheduling iterations before it gets enough GPU time. Its time to first token becomes much worse. So the scheduler cannot give unlimited priority to either side. Processing the whole prompt in one go can interrupt active streams. Continuously prioritizing decode can leave new prompts waiting for too long. The problem becomes more visible when prompts lengths vary significantly. A short prompt may fit between decode iterations without causing much disruption. An 8000 or 30,000 token prompt can occupy the GPU for much longer. The serving engine need a way to process the new prompt without pausing decode for one large uninterrupted period. Chunk prefill handle this by splitting the prompt into smaller pieces. Instead of processing all 8000 token in one operation, the scheduler processes part of the prompt, then returns to the active decode sequence. The first chunk of the new prompt is processed, then the existing sequences gets another decode step, so each one can generate its first token. After that, the scheduler processes another part of the prompt followed by the another decode step. This continues until complete prompt has been processed. The existing request keep receiving output tokens, and the new request also keep moving through prefill. Inference engines usually control this using a token budget for each scheduling iteration. Suppose the scheduler has a fixed number of tokens it can place into the next model execution. The active decode sequences consume part of that budget because each one needs another token. The remaining capacity can be used for a chunk of the new prompt. You do not need the exact budget calculation to understand the mechanism. The important part is that one large prompt is divided across multiple iterations rather than taking over the GPU for one long period. The size of the prefill chunk still matters. If the chunks are very large, each iteration takes longer and active streams may again see noticeable pauses. If the chunks are very small, the prompts needs more scheduling iteration before prefill completes. That can increase the new request's time to first token and create more scheduling overhead. So the engine chooses a chunk size based on the workload and the latency it wants to protect. An interactive chat system may prefer smaller chunks because a smooth streaming matters. A batch workload may accept larger chunks because overall throughput matters more than the delay between the individual tokens. Chunked prefill allows both kind of work to keep progressing, but the scheduler still decides how much of each phase enters the next iteration. In production, measure time to first token and inter-token latency separately. A request can have good TTFT but poor streaming latency if long prefills keep interrupting decode. It can also have a smooth token generation after waiting a long time for prefill to begin. Prompt length distribution is also important. Average prompt length can look normal, while a small number of very long prompts create latency spikes for many requests that sharing the same GPU. So when the user report that a streaming sometime pauses, look at which prefill jobs were scheduled at that time, how large those prompts were, and how much prefill work was allowed into each scheduling iteration. Every LLM request begins with prefill and then moves into decode. Prefill processes the prompt and determines when the first output token can appear. Decode generates the response one token at a time and determines how smoothly those tokens arrive. When both phases share the same GPU, a long prefill can delay active decode, while a strict decode priority can delay new request. Chunk prefill splits the prompt into smaller pieces, so the scheduler can continue serving active sequences, while the new request also makes progress. At larger scale, some systems separate these phases onto different GPU pools. One pool handles prefill, another handles decode, and the KV cache has to move between them. See you in the next one.